Good day, everyone. My name is Lorraine Tuan. I am from Western Mindanao State University, Zamboanga City, Philippines. I am the presenter of paper number 123, and I am deeply honored to present before you today at this esteemed conference. Our paper is titled HatchMore, a portable egg incubator with multi-egg handling and Bluetooth-enabled monitoring for enhanced hatchability. Let me introduce the authors of this paper. I am Lorraine Kate M. Tuan, and together with me is Miss Christine May Chong, Miss Wensley Kate L. Francisco, Mr. Ralph S. Hibionada, Engineer Kevin Mark A. Bejarano, a faculty from Electronics Engineering Department, and Engineer Januber Garcia from the Mechanical Engineering Department of Western Mindanao State University. To guide you through our presentation, here's a brief outline of what we'll be covering today. First is an introduction, gaps and research objectives, followed by the methodology, results and discussion, and the conclusion of the study. Now let's start with the introduction. The poultry industry is a vital sector of agriculture in the Philippines. It significantly contributes to the country's food security, rural employment, and economic development. Poultry farming involves many processes, and one of the most crucial is egg incubation. According to a study by Archer and Cartwright 2017, egg incubation is the process of maintaining optimal levels of temperature, humidity, ventilation, and egg turning to ensure the proper development and hatching of fertile eggs. Traditionally, this process has been done manually, either by hands or with makeshift incubators using light bulbs, particularly in rural areas of the Philippines. A major challenge in egg incubation is the low hatch rate, often experienced by poultry farmers primarily due to inconsistent environmental conditions. To address this issue, artificial incubators have been developed. These incubators provide a more controlled and optimal environment compared to traditional methods. To standardize the use of incubators, the Philippine National Standards has established technical guidelines for the design and performance of egg incubators used in the country. Incubation for chicken eggs typically lasts for 21 days, and that process is divided into two main periods. Setting period, which is from day 1 to day 18, and hatching period from day 19 to day 21. During the setting period, the temperature should be maintained at 37.5 degrees Celsius with a relative humidity around 58%. Eggs must be turned 4 to 6 times a day at a 45-degree angle. Turning should be completely stopped once the hatching period begins. In the hatching period, the temperature should be adjusted to 36.9 degrees Celsius and the relative humidity should be around 66 to 75%. Maintaining these parameters is critical as environmental fluctuations are a leading cause of low hatch rates during incubation. During egg incubation, identifying the egg's fertility is essential. According to Garcia and Maguili 2021, egg fertility is monitored through candling, where eggs are placed against a light source to check if a developing embryo is present inside. In most poultry farms, this is done manually. Despite being effective, manual candling is a time-consuming task and prone to human error. This process also requires the removal of each egg, which exposes the egg to temperature and humidity level fluctuations, which may disturb the egg's development and reduce hatchability, as stated in the study of Adegbenho et al. 2020. In recent years, artificial incubators with automated system has become more common. Modern incubators are now introduced to the public, equipped with sensors for temperature and humidity regulation, ensuring optimal conditions during incubation. A study done by Zhang 2020 says that an automated control system can regulate and maintain critical parameters, promoting less human intervention and increasing hatchability. A monitoring system is also a valuable feature for an incubator. A study by Doles et al. 2023 demonstrated the effectiveness of an IoT-based monitoring system using BLE technology for real-time data collection. Bluetooth Low Energy or BLE is a wireless communication technology that allows devices to exchange data over short distances using minimal power. In egg incubators, BLE enables real-time monitoring of temperature and humidity through a connected mobile app without needing constant power or an internet connection. Now let's move on to the gaps of existing studies. Existing smart incubators primarily still requires the use of manual candling for fertility detection. It lacks integrated fertility assessment, limited BLE-based monitoring solutions, and user accessibility issues. Similarly, while some research has explored IoT integration for remote monitoring, a gap often remains for a portable, cost-effective solution that seamlessly combines robust environmental control with efficient onboard multi-egg fertility assessment and user-friendly mobile monitoring. These existing solutions may also not offer the same level of comprehensive data logging and visualization in a dedicated mobile application focused on small-scale usability as envisioned with HatchMore. Based on the issues and gaps identified, the primary objective of this research is to develop a smart portable egg incubator to achieve an efficient and sustainable chicken egg incubation process with optimal hatchability rates. More specifically, it aims to develop an automated system for temperature and humidity control, integrate a built-in candling system for efficient fertility detection, implement BLE-based real-time monitoring for data transmission, and evaluate the incubator's performance on incubating fertile eggs successfully. Now let's move on to the methodology of the study. Figure 1 presents the conceptual framework of the HatchMore incubator designed to deliver an efficient and automated incubation process. Figure 2 on the right presents the system process flow, which automates the regulation of temperature, humidity, and egg turning schedules during the setting period to ensure optimal incubation conditions. Figure 3 presents the system architecture of HatchMore Incubator. The ESP microcontroller serves as a central controller, facilitating automatic regulation of temperature and humidity, egg turning mechanism, and a built-in multi-egg handling system. A DHT11 sensor was used to monitor the temperature and humidity, crucial for maintaining an optimal environment for the eggs. A PTC heater served as the heating element, and an exhaust fan and water basin was integrated to facilitate cooling. You can see on the right, Figure 4 is a prototype design of HatchMore Incubator. For the software development, the incubator's software system was programmed using Arduino IDE, while the HatchMore mobile app was programmed using the MIT App Inventor. For the testing and validation, the HatchMore incubator was tested to assess its ability to facilitate egg incubation. The system was tested using two batches with eggs categorized based on storage duration prior to incubation. Now let's move on to the results and discussion of the paper. First is the accuracy comparison of multi-egg candling and manual candling. This comparison is done to determine if the multi-egg candling offers a practical advantage than the manual candling in terms of fertility detection. You can see on the table 2 that the eggs were labeled F and I, F for fertile and I for infertile. For the first trial, the manual candling accurately identified all 23 fertile eggs, while the multi-egg candling misclassified 4 infertile eggs as fertile. For the second trial, the manual candling correctly identified 3 fertile eggs, while the multi-egg candling misclassified 3 infertile eggs as fertile. Both methods also identified one cracked egg during the second batch. No fertile eggs were classified as infertile in both trials. For the first trial, the accuracy rate of the multi-egg candling is 92.86. For the second trial, the accuracy rate of the multi-egg candling is 94.54%. Next is the time efficiency comparison of multi-egg candling and manual candling. This comparison was done to analyze and determine whether the multi-egg candling system offers a practical advantage for the fertility detection part of the incubation. To determine the time efficiency, the time taken in manual candling and time taken in multi-egg candling was compared, and after applying this formula, it was determined that the time efficiency for multi-egg candling is 356.67% higher than the manual candling time. Now let's discuss the hatch rates of the first and second incubating batches to evaluate the overall performance of HatchMore Incubator. To determine the hatchability rate, the number of hatched eggs is divided to the number of fertile eggs times 100. For the first trial, a total of 21 eggs hatched into chicks out of 23 fertile eggs, attaining a 91.30% hatch rates for the first trial results. For the second trial, a total number of 34 eggs has hatched out of 36 fertile eggs, attaining a 94.54% hatch rates for the second trial. The hatch rate results of both trials suggest that the incubator provides an optimal hatching environment, reducing the risk of embryo mortality. Presented here is the temperature and humidity trends throughout the incubation period through the BLE mobile app. The figures illustrates the fluctuations in temperature and humidity changes from day 1 to day 21. As a conclusion, the HatchMore Smart Portable Incubator addresses traditional incubator issues through automated temperature and humidity control, creating an optimal environment for embryonic development. It achieved a 91.30% hatch rate in the first batch and 94.54% in the second trial. The automatic candling system reached a 93.7% average accuracy, reducing manual handling and potential embryo damage. The BLE-enabled mobile app enabled real-time monitoring and control. Overall, HatchMore provides an automated, cost-effective, and sustainable solution for small-scale poultry farming, standing out with its integrated multi-egg candling and advanced BLE-enabled monitoring features. This brings us to the end of our presentation. We hope that the findings and insights we've shared today have added value to the ongoing conversations in this field and offered useful perspective for both research and practice. Thank you all for your time and attention.